The Minimax algorithm implements recursively the idea of the minimax, that function that actually tries to find the best moves for max to maximize its utility. So remember that max and min are both playing against each other, and both of them are playing optimally. The Minimax algorithm implements the minimax function we just saw as a recursive algorithm that actually allows to find the best move for max. Remember that both max and min are playing optimally, which means that max is trying his best to find the maximum utility in the leaves, while the min is trying to find the minimum utility in the leaves. So this is a recursive function that's actually three pieces. The function decision, that actually the main function, that's actually the main function. The function maximize and the function minimize. Initially, we start with max, so we are going to call the function maximize. The function maximize actually finds the state with the highest utility. This is max's job. And the function minimize will try to find the child with the lowest utility. This is min's job. All right, so the function max, initially we start with the initial state we call max. If it's a terminal test, then we are going to end the function. Otherwise, we're going to look for in the children for the maximum utility children, right? So we're going to pick the maximum child among the children by doing a recursive call. So this function is going to call maximize because we're going to give a turn to min, and min is going to give a turn to max, and so on and so forth. So it's going to call minimize, and this function minimize is doing similar thing. It's going to check if it's a terminal. Otherwise, it's going to explore the leaves and take actually the leaf or the node with the minimum utility. So again, it's going to search here for the minimum utility. It's going to put that in a tuple. All of them are actually using a tuple. Max child, max utility for maximize, min child, min utility for minimize. But keep in mind that one is trying to find the child with the highest utility, the other one with the lowest utility. So it's going to be bouncing off between maximize, minimize. So until we actually reach the leaves, in which case we're going to return these values up to the node that's the root. So basically, the function at the end will return the child with the highest utility for max after the recursive execution is done, which means that we went all the way deep into the leaves and we reached the leaves. That's how Minimax algorithm works. Because of its recursive nature, it's easier to explain Minimax algorithm through an example. So let's take an example of a game tree in which we have max and min taking turns. So max will start first. So max is generally represented by a triangle with the point going up. So each of these lines is called apply. Actually, it's called apply. So this is a multiply game tree. So remember, it's a DFS. We have to go all the way through the leaves to reach the utility values at the leaves, and then brings them back up. So the utility, the terminal values or the utility at the leaves is given by these numbers here. Max will take a turn, will actually brings up the value between 2 and 9, he will pick the value 9. Between 7 and 4, it will pick the value 7. So it's going to maximize, take the child that actually maximizes the utility. So the values will be 9, 7, 9, and 5. Min, we try to not let max get the maximum of the leaves. So it's going to take the minimum of the leaves. So the min in this case, we'll pick 7 among the 9 and 7. We'll pick 5 among 9 and 7 and 5. And at the end, max will have the choice between 7 and 5. So it will pick the maximum value of 7 in this case. So the edges or the arrows here are actually representing the actions taken by max and min successively. So max will start by picking up this action. After thinking about going all the way in the leaves and bringing this value up, max will pick this action, min will pick this action, and then max will pick this action. This is when both of them play optimally, this is the best choice for max to get maximum utility. And the child with the maximum utility will, in this case, is this child with the value 7. So how about the Minimax algorithm properties? So first of all, it is optimal. Assuming that both opponents are playing optimally, the algorithm is optimal, and it's also complete. It will find a solution if it exists in finite trees. Minimax, it performs a DFS, so it has DFS time and space complexities, where B is the branching factor and M is the maximum depth of the game tree. So as examples, let's check tic-tac-toe chess and go to see what would this time and space complexity represent. So for tic-tac-toe, which is one of the simplest game out there, we saw that actually it's even on the board, we can't really draw the whole search space. This is because we have about a branching factor of 5, which is the average legal number of moves. With total of 9 moves, which means that we have 9 plies to fill actually the tic-tac-toe board. This represents 5 to the 9. This is the complexity in time, which represents about 2 million of nodes that we need to explore. Regarding this, the number of terminal nodes, we have about 9 factorial. This is the number of terminal nodes that we could reach tic-tac-toe. So tic-tac-toe is an easy game for AI, let's say it this way, as compared to chess that actually has a branching factor that's an average of 35. And that actually typically the games in chess reach 100 ply, which means that we have a b to the d, which is 10 to 154 nodes that actually represent its time complexity in order to explore the full search space. This is pretty much impossible. That's why there have been many heuristics that were designed in order to search a chess and not having to go all the way to a depth of 100. For Go, we have a branching factor that starts at 391, which may seem like a hopeless AI to build for the Go. For 19 by 19, we have a branching factor of 361. You could imagine what would be the search space size. It's absolutely huge. But it was still solved by AlphaGo, so there is always progress, which makes actually games really a challenge for AI to solve. Such a huge search space or state space represent actually a big problem to implement for real games, because we are limited in time. We really can't wait forever for our opponents to make a move on a chessboard, for example. So it's impossible to really search the leaves because of the depth and the branching factor of those real games. And to be practical and run in a reasonable amount of time, Minimax can only search to some depth. So it's not reasonable to get into a depth of 100, for example, for chess. But we know also that more plies make a big difference. If you can really think ahead and go as deep in your thinking about your opponent actions and then the consequences of the actions by your own actions and so on and so forth, more plies make a big difference because you can plan better when you know more about the different consequences of those choices of actions. The solution for this big problem is to replace terminal utilities with an evaluation function for non-terminal positions. So remember, Shannon has suggested initially to cut the search earlier because there is no way, again, we can get all the way down to the leaves. So let's stop earlier and have an evaluation function that tells us roughly how this position is actually doing in terms of evaluation function. And then also what we could do is to use iterative deepening search, which means that we're going to try to go deeper, deeper, deeper. And when the time is off, what we can do is to take the solution that comes in the previous iteration. And finally, what we can do is also use pruning, because we have a huge search space. Maybe it's possible to prune it and not have to explore everything. So if we can eliminate large part of the tree, we can go in the same amount of time deeper in the game tree.